An ideal gas is a small, unbreakable, dense sphere. It collides with everything elastically, so it doesn't lose energy or momentum. That includes the walls of any container holding that gas. An ideal gas is a strange object. It can be changed and studied in any way you can imagine, because it is really an elaborate thought experiment. If you change the force of the gas on a wall, you simply make it move faster. If you want there to be more force, then you add more particles hitting the container. These changes can affect the container in one of two ways. You can either make your thought experiment so that the wall of the container doesn't change, or you can allow it to change on collision. If you allow it to change, then you have allowed your ideal gas to exist within a changeable volume of space. Because the gas can force the container to change shape, then the gas can also take up more volume. Of course, if you left your ideal gas container there, your gas would shrink down again and leave a vacuum behind inside your container. So you imagine the container itself has a tendency to shrink back down on itself until it follows the contours of the gas cloud. This is where you need to have a bit of imagination, because in order to shrink down the container would need to exert a force of its own, which it doesn't in an ideal gas arrangement. The container is there only to define the edge of the gas cloud and what happens to physical properties at this boundary. The volume of an ideal gas, therefore, can be described as the volume of this imaginary container surrounding the gas cloud. As the gas cloud gets bigger, the volume of the container gets bigger. As the gas cloud gets smaller, the volume of the container gets smaller. As with the area of a wall of a container, the volume of the container follows standard mathematical principles. The container can be any three-dimensional shape, as gases expand to fill all shapes. If the container were a sphere, then the volume would be 2/3 pi r cubed. And if it were a cube, it would be length times width times height. What is interesting is how volume interacts with the other properties of an ideal gas, described in other podcasts. Remember, the volume of an ideal gas depends on two things: the temperature and the mass of the gas. In other words, the number of gas particles within it. But we'll see that more in future podcasts.